So my name is Joe Chop. I am the site reliability manager for the Pacific side of the world at Shopify. So if you can see, smell, or drive to the Pacific Ocean, you're probably on my team. We have folks in Japan, Singapore, Hawaii, where I'm from, as well as hopefully Australia soon. So if you're interested, please reach out to me. We do a follow the sun rotation, so no getting woken up on our team here. Like I said, I'm in Hawaii. I like to surf. I like to walk my dogs, but I also have claim to commanding the most severe incident in Shopify's history. It's obviously something we probably don't usually claim, but at Shopify we take a lot of pride in our retro process and reflecting on past incidents and learnings, and that's where a lot of inspiration from this talk came from. I attend probably hundreds of retros at this point at Shopify, and there's always a common theme of like a lot of developers just don't understand the basics of resilience, or they just weren't exposed to it earlier in their careers, myself included. I was a software engineer for about 15 years until I moved into the operations side of the house, and until you see things fail, you kind of don't know about them, right? You don't know until you see something kind of catch on fire, and so the talk today is really just revisiting some basics, whether you've been in this space for a while and you need to revisit some of the fundamentals, or you're moving into SRE and you want to go home and make your service more resilient. So it is entitled The Multi-Layer Cake Resilience. Bear with the metaphor. It's not great, but trying. So for those that don't know what Shopify is, not Spotify, we are an e-commerce platform, so we enable merchants to basically go from 0 to 100 in one day, right? They can spin up a custom storefront, add product, add collections, buy a domain, and start selling right away. Last weekend was our was it last weekend? Yeah, I think it was last weekend. I've lost track of time, but our busiest weekend for probably many of those that are in e-commerce, especially for us, we did $7.5 billion in sales. From the engineering point of view, that was 76 million requests per minute at the edge. Lots of stuff in between, translating to 14 million MySQL queries per second at our peak across multiple shards. Obviously, we must have a pretty complex architecture to get there, but in reality, if we zoom out, it's actually quite simple. So it's just 3 boxes. We have some edge request stuff. Requests come into the edge. We do some logic. We send it to an app server. It could be microservices in many cases. In our case, it's the monolith, but it goes down to the app. App does some fancy stuff, and then it probably needs to save some data somewhere. In our case, MySQL. It could be other databases at other companies or other methods, but really it's that simple, right? We have kind of 3 different layers, and we like to think, our world is like this, where we have a nice pretty cake. Don't mind the bleeding icing, I guess that's, I don't know what that is, but nice pretty cake, nice and upright, beautiful, delicious cake. But in reality, like, this is our life, right? Most of the time, the SRE on call, we're hoping that this doesn't happen, right? We're making sure that the cake, our systems, they stay up, they stay reliable, they're not knocking over, they're not tipping over. I'm sure we've all felt this many, many days in our lives. So here are some principles that we can do and keep in mind. Really just take home easy things we can take home and do today without very much effort at all. So the number one thing you can do, easiest couple minutes, is like set timeouts at all layers of the stack. At Shopify, if we look at the edge, we use NGINX. There it's very easy, and we kind of set our timeouts very high and very generous at 60 seconds. That's essentially just to make sure that the request actually comes back at some reasonable amount of time. But you'll usually want to start something higher at the higher layer of the stack. As the request moves down the system, at the app server, we use Ruby on Rails app, so we have rack timeouts. You'll probably want to set a GraphQL timeout there as well to make sure those don't run away. And then really the easiest one, which is probably the most forgotten one, is like outgoing HTTP calls. Whether you're using like Faraday or Request.js, they generally all have very generous timeouts, something like 60 seconds. There's no reason to ever wait 60 seconds for an HTTP request, especially if it's something in the hot path like shipping rates, payments, a user is going to leave a lot quicker than 60 seconds if they're waiting for shipping rates to come back. So there's no point in waiting 60 seconds for those type of calls to come out. When we look at the database layer, this is where we definitely want to be more stringent. We use MySQL at Shopify, and so there's a couple of techniques you can employ there. We use PTKill, which is essentially like a sidecar that watches queries, and when they exceed a certain timeout, you can either log out a statement for observability if you're not really sure if it's safe to kill, or you can actually kill it via PTKill. The other one that we use is MySQL max execution time. So this is the database engine actually killing the queries. And so for some of our critical paths like checkouts, we have very strict timeouts, 2 seconds. Is it coming in and out? We have strict timeouts there, but we also have dynamic timeouts as well. So for queries that are in our, no, I shouldn't say that, like our FICO list, our naughty list, we have more dynamic and longer timeouts there that we dynamically inject. So number one thing, again, timeouts. Kind of extending that concept is circuit breakers. So not only do we want to fail fast with quicker timeouts, but we also want to back off when there's a slow or down service. There's no sense in sending requests to a service that never has a chance to recover. It's very much like a circuit breaker in an electrical system. If there's a faulty outlet, there's no point in sending electric to that outlet. It's not safe. It's a waste of resources. And we have that same principle in software, except for that we obviously want those circuit breakers to be automatic and not having us go down to the breaker box to flip them. So at Shopify, we use a library. So you can implement this at all layers, but at the app server layer, we do it via a library called Semion. It's a Ruby library. We use it to protect downstream resources like HTTP endpoints, MySQL, Redis, Elasticsearch, really all of our critical data stores and dependencies. We have Semion guarding it there. I don't know what the monkey is holding the banner for. I wish it was a cake for the purpose of this talk, but that is the logo for Semion. So finally, the last principle. So we had timeouts, circuit breakers, and then just a generic capacity control. And the idea here is really boils down to a basic principle in queuing theory, which is Little's law. It's very simple. The average number of items in the queue is equal to the number of items arriving times the average waiting time in the queue. The easiest metaphor of this is like a coffee shop, right? You can have the best baristas in the world making coffee. You can find the optimal number of folks to make coffee, and maybe they can achieve 10 coffees per minute, right? You're very popular. 100 people show up to the coffee shop per minute. Most people aren't going to want to wait more than 5 minutes for a coffee before they just leave. And so if you have 100 people arriving at that coffee shop, but you can only make 10 per minute, customer 51 is going to be mad, 52 is going to be mad, 53 is going to be mad, 54. After the first 50, or after that first 5-minute block, there's no hope, right? You have to start shedding load somewhere, right? Or limiting the number of people actually entering the coffee shop. So that's the basic principle that we do at multiple layers. And at the edge, we start with basic DDoS mitigation. So these are like things like sneaker bots, credit card testers, things like that, where it's just truly bad traffic that has no business at the app server layer, where we just generically block those type of traffic profiles. At the app server layer, we do other smarter techniques. So checkout throttle is, again, controlling our most critical path of Shopify, which is checkout. We understand, we want as much checkout traffic as possible, but at a certain point, we have to start denying customers. In this case, actually not denying them, but throttling them, so giving them a ticket to come back later. So that sort of capacity control. And then other limits, such as like API client limits. Again, on some of our heavy endpoints, there's an upper bound. There's only so much coffee we can make per minute, and so we have to throttle it there. Otherwise, the customer or the user is just going to be upset, right? So it makes sense to trade off the arrival rate versus the success rate. So now we're going to jump through a couple simulations just to see what this looks like. Oh, I can't believe it works. Okay, excuse the front end. This is what happens when an SRE tries to make a front end. So here we have like just a basic view of a system. We have a user. We have an edge layer. It's stateless, so there's two different edges. We have a stateless edge or app server that's scalable, but we're just round robin requests, and then we have a database writer. So this is kind of like the bottleneck of our system. In this scenario, probably in many systems, your writer or you're going to have a single point of failure at some point. Okay, so now we're going to talk about a slow query degradation. All right, everything is fine. We can see that we have some SLOs now. So the first number on all these is like a % SLO, then the latency at the particular layer. Nothing crazy at this point. The edge is pretty quick. The app server is long. Database is 50 milliseconds. Queries, not bad. All right, so now a slow query path emerges. Here we can see the database is slow, but the app servers are still fine. So the query time went up from 50 seconds to 150 seconds. SLO starts to be violated. At this point, what's going to happen is you're going to have back pressure at your app servers, right? Your app servers are now taking 1.5 seconds for every request going to the database. Now they're taking 60 seconds for every request to the database. By allowing those query times to run out of control at the database layer, you're now just moving the pressure up in the stack. So now you have not one problem, but two problems, right? Now your app server is running out of capacity. Same principle. The database goes down, your app servers are queuing. Now your edge is going to start queuing. Bye-bye edge. So very simplistic oversimplification of what happens, but I can't tell you how many times I've been in incidents where they just let a query run out of control, consumes the app server, consumes the edge, nothing is usable. So in the simplest sense, it's very easy to get over this, right? We're back in the same scenario. That slow query comes back, but at this point, we're capping it at 2 seconds, right? So we have that max execution time at the database layer for 2 seconds. We're taking the hit on correctness, right? Those queries will never succeed if we're failing them. But the trade-off is better, right? The app server is still stable. The edge is stable. We can still serve 2% or 98% of all requests. We're just really making that trade-off. It's better to serve a failed request than a slow request and really prevent that cascading failure. All right, so here's another scenario. Also been in plenty of incidents like this, where we're not talking about a single slow query, but perhaps the entire database is slow. Maybe it's a network that went bad in that zone or disk I/O for that database, so the entire database is slow. We're back to everything is fine. In this case, we now see we're back in the same failure state as before. We have some timeouts now. We learned from our previous mistake. So at least the database, they're timing out after 2 seconds. We have a much higher failure rate. We're having like 50% of queries are now failing. Of course, we're going to have that knock-on effect where if the app servers are waiting 2 seconds for 50% of the queries, the app servers are going to take longer to process requests. That's cool. We got auto scaling. We'll just throw more servers at it. Oh, let's add some more. This will of course work, right? Maybe more. Still at a bad state. Everything pager's still going. Okay, now finance is mad, right? We're just adding servers at a problem that it's not going to fix anything. The database is at 50%. You can't just add app servers to compensate for a bad database. And this is a very common scenario where if you don't sort of have controls in this place, your autoscale will just run out of control. It thinks it's working harder than it actually is, but we scale unreasonably. All while, again, not letting the database a chance to recover. So here we have, this probably doesn't show up very well. Oh, kind of. You can see my CSS hack there of a little bit of a circuit breaker on the edges of the gap servers, the color black indicating that it's closed. So in a healthy state, right, we're back here, the database gets slow. The app servers will continue to take longer. In that first wave, right, the app servers need time to react to the failure state. But at a certain point, those circuits will actually open. The app servers will choose not to send the request to the downstream database. It knows the database is most likely going to fail, so it's just not going to bother. The red indicating an open circuit. So what we see now is latency has actually restored at the app server layer. Because we're failing quick, we're not waiting 2 seconds for all those queries to hit the database. We're actually recovering our latency at the app server. Correctness is still wrong, right? Those queries aren't working, but at least we're not wasting resources. At least latency is not up. We're not scaling up for no reason. SRE has changed the underpants. I don't know if you've ever seen a writer go down, but it's pretty painful, especially when it does things like checkouts and other important things. Worst type of instance, I hate when writers go down. Maybe the writer failed over, maybe just to back off a load, let it recover, whatever. At some point in time, it'll come back. You'll probably see a slow recovery where maybe one of the circuits will close, the other ones will start to close later, and we're back in a safe state. So again, if that's all done automatically, including the failover, it really lets you recover from those blips of latency, of I/O failure, whatever. Let's see, do the last one, and then, so we talked about timeouts, circuit breakers, and now we're going to talk about capacity control. So here we have a third-party app hitting a heavy endpoint. It hits it hard, real hard. Everything is fine, so we're back in the steady state. So now we have some requests coming in. We have 100,000 requests per second coming in at the edge. It gets distributed across the app servers, and then it's all funneling back in to the database. Very simple, one request, one query. And that's cool, everything's great. But the client sends more, right? Everything's succeeding, let's just send more. 130 requests per second. All right, database is holding up, it's running hot, right? We see latency going to 250, 99%. Not great, but we're holding in there. App servers are hanging in there, there's latency there, but nothing's on fire. At some point, we're probably going to hit like a nice, steady peak before things start tipping over. In this scenario, we're there now, right? We're really at the happy redlining, if you will, of the car's not on fire, but it's maxing out. But the client says, whatever, stuff is still succeeding, I'm just going to hit, I'm going to throttle, right? Or I'm going to hit the gas. It sends more. We're now up to 160 requests per second at the edge. We can see we're sending those requests to the database. So we went from 43,000 requests per second to 53. And we're going to have that same knock-on effect, right? Things are going to start slowing down at the database. They're going to start queuing at the app server layer. They're going to start queuing at the edge. If we go back to that scenario of the coffee shop, we're doomed, right? We already know we've hit the red line at the database. We have to start shedding load somewhere by allowing unbounded access to a database path. You're doomed for failure. Again, it's completely out now. I can yell. Now? I think it's the ones on the left that are working. This one? Yeah. Hello? Yeah. Right. I'll go like this. So now we're looking at the solution. This one's actually very simple, right? We talked about it. We alluded to it. Once we hit that max stable throughput, the client gives it more juice. At the app server layer, we just prevent those requests from coming in. Maybe it's a basic ticketing system where we count either requests to the database layer or ticketing by client. There's multiple ways that we can actually control it there, but by preventing those requests from actually ever going down the database, we maintain that stable throughput to the database. I don't think that's working anymore. But, so those are the three scenarios. I've seen all those three principles failed multiple times at Shopify. We obviously try to automate all of that away so the developer doesn't need to think about it. But end of the day, it's really important that developers are aware that these systems are in place behind the scenes. They take a massive exercise of tuning them correctly. And ultimately, we always have to remember it's these resiliency techniques that keep the cake up. So let's try to avoid the knocking over. That's all.